Hey everyone, welcome to University of Winnipeg Chemistry 1112. Dr. Carroll here. We're looking at the first lecture of Chapter 21, Nuclear Chemistry and Radiochemistry. We don't need that in the foreground, do we? So, here we go. Introduction will be some reminders of stuff back in grade 6. I don't know, stuff with the guts of an atom, and then we go from there. And so, recall, as I look on page 1021, that we haven't really paid much attention to the possibility that a nucleus is a structure that can change. We've assumed it can change. But if the conditions are right, nuclei themselves can undergo transformations that can change their structure, and in so doing, release a heck of a lot of energy. That's why we have nuclear power. That's why we have nuclear weapons. So let's look at the structure and the energetics of the nucleus to get things rolling here. So most of the mass of an atom is contained within the nucleus, and the volume is essentially that of our smeared out electron probability cloud. There's lots of creatures that pop in and out of a nucleus. Protons and neutrons are the two main ones we talk about, and they're called nucleons. There's other ones that come in and out, hadrons, tau particles. Electrons can be created within the nucleus. We'll look at that a tiny bit. Positrons, and but the main ones are the protons and neutrons. Protons charge one atomic unit or electrostatic unit, AU or ESU, which is 1.6 by 10 to the minus 19 coulombs and a mass of 1.673 by 10 to the minus 27 kilograms. Neutron has no electrical charge. Its mass is essentially the same as a proton, slightly more, 1.675 by 10 to the minus 27th. So these free protons don't last long. They capture an electron, become a hydrogen atom, and free neutrons, which are generated in the course of a nuclear reaction, don't last long either because they can be gobbled up by the nucleus, and that'll lead to a nuclear-induced fission, which we'll look at again a little later in this chapter. So here's a table, 21.1, where we see the main pictures we're looking at: a proton, a neutron, an electron. An electron we usually write with an E minus. I don't know why they didn't put the minus in there. Let's see. Yeah, well, they should. There's the charges. An electron is just opposite charge of a proton. Not opposite mass, though. It's just around a 2,000th of a mass of a proton. Then, if you ever wanted to know, the molar mass in grams per mole of a proton and a neutron are around 1 each, and then electron much less. Electron is also called a beta particle, and the book just says beta, but we'll write it as beta minus where we can, because there's something called a positron, which is going to be written as beta plus, which is an anti-electron, so it has a charge of 1 electrostatic unit, or 1.602 by 10 to the 18th, and the mass is the same as the electron, 0.000911. So a positron is not the same thing as a proton. Each particle, each kind of nucleus is called a nuclide, which is hard to say. They are characterized by how many protons there are, which is Z, the atomic number, and the neutron number, which is capital N, which I know is used for Avogadro's number and a bunch of other stuff. But each nucleus will contain Z protons and N neutrons, and the mass number is going to be A. So A equals Z plus N, and if you have the same Z but different N, then you're talking about isotopes. Some elements have just 1 or 2 isotopes, and some have like a dozen. So different elements have different numbers of isotopes, and there's no magical formula to decide, to predict how many isotopes there are based on how many protons and neutrons there are. Okay, and because there's different isotopes, there's different properties associated with them. Students sometimes get confused with the mass number. They say it's the same as the average atomic weight that they'll see, or average atomic mass they'll see on a periodic table. By the way, you should all have a periodic table handy with you. For this chapter, we use it a lot. And the truth of the matter is that the mass number is for a specific nuclide. It is not a weighted average of all the isotopes of a given element. So the mass number is an integer, a positive integer, 1 or larger. Okay? Mass number is, average atomic mass is also a positive number, but it's got decimals involved with it. Okay? We use the average atomic mass more when we talk about stoichiometry and that kind of stuff. Now, A is always close to the numerical value of the molar mass. I mean, it's not that far off. Fluorine has, okay, what kind of fluorine? Well, here's fluorine 19. This is the way to write it. So 9 is Z. If I'm talking about the fluorine 19 nucleus, sometimes you write F-19 written as that, then it has 10 neutrons and 9 protons. So 10 plus 9 gives me 19, and 19 is the mass number for the fluorine-19 isotopes. Now, there could be other ones. This book was a little shady there. You shouldn't have just written fluorine. You should have written the fluorine-19 isotope. So its mass number is 19, and its molar mass is pretty darn close to that, 18.998. But it's a different concept. And here we see some examples here. We got copper 63, helium 4, carbon 12. These are all nuclides. Carbon 63 would have 63 minus 29. Let's see, 63 minus 30 is 33, but it's one less than that. So 34 neutrons, 2 neutrons in helium 4, also called an alpha particle, 6 neutrons in carbon 12, the most stable form of carbon. And sometimes when you draw these, you won't put the atomic number in there, because you could just look at the periodic table to get that. Okay. I can hear you guys on the phone. Okay. Okay, guys, I can hear you and I'm recording. Okay. The whole world now has just heard a discussion between various family members in my family. So hopefully, just go off the speakerphone. Okay. We're having too much fun here. Element symbol identifies Z, so the subscript's often omitted. Right, like I said, so you could have copper 63. And then we have some other examples. So let's look at some examples of nuclide symbols, just as we get things going. And so I have my periodic table right beside me here. Write the nuclear symbols for the following. The one that contains 92 protons and 143 neutrons. 92 protons is going to be protactinium. There's one we don't hear much. Oops. So it's got Pa. So 92 and 143 neutrons. So I'm going to add them together. I'm not looking at the answers yet. I just want to do it off the top of my head, right? Do it live. It makes it much more exciting. 235. So this is the Protactinium-235 Nuclide. Sometimes it's called isotope. We don't know how, there's more than one. My guess is for these ones up in the 90s and 100s, you're going to have more than one isotope. Carbon isotope with 8 neutrons, well, carbon 6, so I can do that in my head. So carbon 14. So we have, why did I say 92 protons was protactinium? Because I'm looking at a smudged periodic table. That's Pa. It's not Pa. It's you. It's not me. It's you. See, I set that up like that. So uranium-235, 92. So there it is. And you see sometimes it's just abbreviated to uranium-235. And the other is carbon 14 with a little 6. Okay? So let's try these ones here. Write the nuclear symbols for the following ones. we have the nuclide with 15 protons and 16 electrons. So we've got a 15 here and a 31 here. And neon with the same number of neutrons as protons. Well, neon has 10 protons, so 20. Oh, there you go. So there's our examples for that. So that is going to help us. Those little basic building concepts of A, Z, and N will help us as we go through things, including this topic right here. There is lots of energy stored within the nucleus, and some people said that humans should never muck around in the nucleus, that higher beings, and you can get into all your philosophy you want, said that we should never as humans muck around, but we did, and that led to nuclear weapons. It also led to nuclear power, right, which many people think is a good idea, some don't, and you could debate all about that, but that's not this kind of course. We just want to learn the amounts of energy and how to calculate it tied up within a nucleus. And there are 4 forces in physics, and one of them is the strong nuclear force, and you have to pour energy in to kick out a nucleon from a nucleus, the nucleons being the protons and the neutrons, and that is known as the nuclear binding energy. So you can make a, if you want to get fancy with it, we can visualize a nuclear formation reaction. Okay, if we wanted to create a nucleus, so you have so many protons plus A minus Z of neutrons, right? Because that's your neutron number, right? If you want to write your neutron number, you can write neutron number is A minus Z. So that will give us our particular isotope. Okay, formally, a proton is written like this, and a neutron with it doesn't have a charge, but it is 1 for the mass number. But sometimes they're just simplified to a P and an N. Sometimes it's helpful to write the whole thing out. Here's fluorine. So we've got 9 protons. If we're talking about fluorine 19, 9 protons plus 19 minus 9 is 10 neutrons. Gives me fluorine 19,9. If you have a stable nucleus, it's more stable than its separated nucleons. So all nuclear formation reactions are exothermic. Okay, you can't carry them out because it's so much energy is involved, and you have to measure this energy indirectly. One way to do that is by relating mass and energy. Oh, this is a famous equation, isn't it? Energy is mc squared. C is the speed of light. So formation of a nucleus releases an amount of energy that is related to the change in mass. So delta E equals delta M times C squared. And so if you have a change in energy, that is proportional to change in mass, the constant of proportionality being the speed of light squares. If mass decreases, the energy change is negative, meaning the energy is released to the surroundings, right? In other words, nuclear reactions in which mass decreases are exothermic. Okay, so nuclear energy is a lot more than in chemical reactions. So let's look at a conversion factor here. Usually masses for nuclei are tabulated in units of grams per mole. So to compute delta E, we rewrite the equation. So delta equals delta mc squared. There's my speed of light. And then I'm converting it to kilograms. And kilograms to grams, and from joules to kilojoules, and put that all in, and you're given this equation. The change in energy is the change in mass, and I'm going to write this on a separate sheet of paper because I'm going to use this a lot. Delta E equals delta M times 8.988 by 10 to the 10 kilojoules per gram. And you'll see some other books and some questions will use other conversion factors. But if you want to know how much energy is associated with 1 gram being changed into energy, well, that's a heck of a lot, isn't it? That's 89, almost 90 billion, almost 90 billion kilojoules per gram. Wow. So a tiny change in mass results in a huge change in energy. If mass is destroyed, if you get delta M is less than 0, then delta E is also less than 0. So you are using energy to bind up a nucleus, and so you have less energy after than before. And the change in mass that accompanies the formation of a nucleus is called the mass defect. And what you do is you look at the mass of the products minus the mass of the nucleons. This reminds me a little bit of delta H somehow, enthalpy. Products minus reactants. So delta M is the mass of the nucleus that we end up with. In this example, they're using fluorine again. So you take this first, you get its mass, sometimes called its isotopic mass. And one way to determine that accurately is using an instrument which you may use in 2 or 3 years, mass spectrometer. And then you subtract from that how many protons there were and how many neutrons there were. So we take our protons, we take our neutrons, we add them together, get that total mass, and subtract that total mass from the fluorine nucleus, and that is the mass in grams. Okay. Now we can talk about the average mass per element or the exact mass. Molar mass is referred to neutral atoms, and we're talking about electrons. So if you really want to be accurate, you have to subtract electrons from Nuclide molar masses. We also know molar masses are weighted average of all the isotopes. Okay. So you can't really work with elemental molar masses. You have to look with the you have to work with the isotopic molar masses. Okay. We provide values as needed for calculation, so you don't have to keep looking at 100 tables for that. So here we go. Let's go to an example because this sounds tricky, but when you get to the example, it's not tricky at all. Most abundant isotope of helium has 2 neutrons. That is known as an alpha particle, helium-42. Okay, there's helium. It's got a atomic number 2 and a mass number 4. And if I use mass spectroscopy, I get a molar mass of 4.00260 grams per mole. So I want to get the nuclear binding energy of this nuclide. Okay. When you bring the particles together, the protons and neutrons, some of that mass is converted to energy, or else it would fly apart. So how much energy is calculated, is determined. So we had 2 protons, so 2 times, there's your mass. And you can't round off here, right? Because then you're losing things. 2 times the neutrons and 2 times the electrons. Because in a atom, you got to include the electrons. Now I've seen cases where they don't include the electrons. To tell you the truth, this book is the only one that does. But anyways, we'll put it in, fine. So we got the total molar mass of the components, and then the actual mass of helium is not 4.032, but 4.002. So the actual mass of helium for isotope is smaller than the mass of the sum of the component particles. So that's the mass defect. That's the amount of mass that is converted to energy. And it's negative. That's why it's called a defect, deficient, defect, minus 0.038. And if I multiply that, grams per mole by kilojoules per gram, so I end up with kilojoules per mole. Okay. Even though the mass difference in this example is less than 1%, the energy difference is 10 to the 9 kilojoules per mole. And the energy change is negative, indicating that the helium nuclide is more stable. Okay. And you just say the binding energy is 2.7 by 10 to 9 kilojoules per mole. Okay, so, well, yeah, this book really does want you to include the mass of the electrons. So I will. Okay. So let's do the same thing for uranium. Uranium-92. Okay. So my delta E is going to be the uranium-238 value, so 238.0508 grams per mole, minus, I have 92 protons, and the proton one was, I'm just going to look in the book here, 1.007276. Plus the neutrons, which is 238 minus 92, 136, isn't it? 238 minus 92, 146. Times the neutrons, which are 1.008665. Plus 92 times the mass of electrons, 0.001097. 0.001097. And so now let's punch them all out on our calculator. And this is going to be in grams per mole. And then we'll multiply by this conversion factor to get kilojoules per mole. Yeah. Okay, so here we go. Work out 238.0508 minus 92 times 1.007276 plus 146 times 1.008665 plus 92 times 0.001097. I get minus 1.98. 46244, fine. And that is going to be grams per mole. And then multiply that by 8.988 by 10 to the 10th. And I get minus 1.78 by 10 to the 11. Depends what you round off here. Now, because I just did my conversion, what did I do to 3? Minus 1.784. By 10 to the 11. Kilojoules per mole. Okay, so you can double check that. The answer to the back of the book might be off a bit. It might be because of rounding. Okay, so I just want to check one thing here. Did they leave off the electron? I want to look at the practice exercise 21.2. Now I'm curious. Always good to be curious, right? Practice exercise 21.2 minus 1.738. I got minus 1.784. Did they leave off the electrons? 238.0508 minus 92 times 1.007276 plus 146 times 1.008665. Now I'm just curious if they left off the electrons. And then I'm going to multiply times 8.988 by 10 to the 10th. And I get minus 1.69. So no, they didn't leave off the electrons. So let's try it one more time. 238.0508 is the product, nuclide, minus 92 times 1.007276 plus 146 times 1.008665 plus, there has to be 92 electrons because there's 92 protons in uranium. 92 times, what's the electron here? 0.001097. 0.0010972. Okay, and then I'm going to keep all the decimals in there and multiply times 8.988 by 10 to the 10, and I get minus 1.784. So, you think they rounded a bit to get the minus 1.738? What if they just did? How much are they rounding? No, their delta M, they have 5 spaces. I don't think that's going to make a difference. 1.98462 times 8.988 by 10 to the 10 minus 1.783. Well, I think they just screwed up because this looks good to me. If you want, we can go over together in class. Okay. We see here that you can sometimes get the nuclear binding energy per nucleon. What's written here is kilojoules per mole in total. If I have a bunch of uranium-238 nuclei, how much is a bunch? A mole of them, the binding energy would be 1.78 by 10 to the 11. If I divide by 238, which is how many nucleons there are, right? Then I could get the binding energy in kilojoules per mole per nucleon. And that is sometimes a useful thing to do. And we see that here on the left-hand side, we have binding energy per nucleon in units of kilojoules per mole. And then we have some nuclei more stable than the other. And you see a cluster down, excuse me, here. This is the most stable nuclides, the happiest ones. We got nickel down here all the way to krypton, 84. So those are some stable ones. And boy, it's a Grand Central Station this morning in the lab, I tell you. So plot of the binding energy per nucleon versus the mass number. So you have most stable nuclides will lie in a region of around A equals 60. So that's important when we go into more details about fusion and fission. Some of us will have gone fission, right? So from the few calculations we looked at, we can see if you got a greater, you can guess, the greater the mass number, the greater the total binding energy of the nuclide. But the overall stability is getting the binding energy per nucleon. Okay. It describes how tightly each nucleon is bound to the nucleus. The binding energy becomes more negative. Okay, so the book here I see wants you to keep using the negative sign, fine. The nuclides become more stable. Okay, turns out the most stable nuclide of them all, mirror, mirror on the wall, what's the most stable nuclide of them all? It is nickel 62. Okay, two types of nuclear reactions that release energy. If you have a heavy nuclide and it falls apart into smaller chunks, it is called fission, F-I-S-S-I-O-N, and energy is released. If you have two lighter nuclides combining together, sticking together, that's what fusion means in this context. It doesn't mean melting like we have in thermochemistry, but it means sticking together. When two light nuclides stick together, we have fusion, and that releases energy too. In fact, more energy than fission. But it's a lot harder to make a fusion reactor than a fission reactor. And we'll get into more details about that later. Example 21.3, I don't like what they do there. I'm not going to bother with it. Or that one there. Okay. Nor do I care about that. So, I'm just remembering stuff that we talk about and stuff we leave off. Energy barriers is not one that we talk about much either. So I'm going to leave that out and jump straight to stable nuclides. So this in your textbook is in the middle of page 1027. So we said that nuclides with mass numbers around 60, or between 50 and 60, are the most stable. But there's many combinations where, let's see, the balance of electrical repulsion and strong nuclear attraction, like many combinations stable for indefinite times, some are decomposed spontaneously. So there's a whole range of things that can happen. For example, all hydrogen nuclides with A greater than 2 are so unstable that only one of them exists even briefly. The other ones, as soon as they're formed, they're gone. Tritium was formed first when nuclear fusion bombs were tested, I think in, okay, here's the reach for the top, what is it? I think in Nevada in the 50s was the first test of a nuclear fusion bomb. So a nuclear bomb as opposed to an atomic bomb, which was a fission bomb, which was a few years before that. Hydrogen has 2 stable nuclides, fluorine just has 1. Tin has 10. Look at all the stable nuclides for tin. Wow. All stable nuclides, as well as some unstable ones, are found in the Earth's crust and atmosphere. Natural unstable nuclides, those unstable nuclides that occur naturally have natural lifetimes longer than the age of the Earth. Interesting. Or are produced, as I said, naturally occurring nuclear reactions. So, a little bit of trivia there. Here we have an important plot. We have a plot of the number of neutrons versus the number of protons. We have a reference line here with a slope of 1, so n equals z, right? So the rise over the run is 1. This is a reference point. Then all these little dots here represent a belt of stability. I've heard it called an island of stability, a peninsula of stability, an isthmus of stability. And so if you're plotting your n, which is the number of neutrons, versus your z, and one of those dots falls in that belt, then you have a stable nucleus. And notice that it is not a 1-to-1 ratio, right? It is for most of the earlier, lighter nuclides, but past calcium, so there's calcium 40, n over z is 1, right? You have 20 neutrons, 20 protons, for the ratio is 1. But to be stable, when you get more than 20 protons, when the atomic number is more than 20, you see how you're starting to veer up, right? The slope is more than 1. You have more neutrons per protons. The neutrons are like the mediators trying to keep the protons from pushing each other apart. And you can sort of have a 1-to-1 case, but if you have it's like a hockey referee. If you got one referee, and that analogy doesn't work, does it? And when it becomes a big brawl, you need more referees because all heck's breaking loose than there are players. No, it's usually less referees than players. Herewith, that hockey analogy has been withdrawn, okay? So forget the analogies, just see, as you have more protons, you need even more neutrons to mitigate the repulsions between the protons to keep them stable. And there are nuclei which are higher than that belt of stability or lower, okay? And if you have an unstable nucleus which is lower than the belt, it means you have too many protons, right? You say, oh, I'm lower down, I got to get higher up. So you want to convert those protons into neutrons. You want to turn that frown upside down, right? If you've got too many neutrons, you have to find a way, like over here, it's unstable, and if you want to become stable, you have to find a way to convert neutrons into protons. And this is where the beta minuses and the beta pluses come in, and I can't remember which one is which, but we're going to go through that and we're going to figure it out together. Here we see a more, near the end here, we got lead 208, which is stable. You know, once you get past 82, then everything's unstable, right? Your belt is finished. It finishes at 82. So we have to find ways to predict if I have an isotope over here, what spontaneous process can happen, which gives off, which radiates particles and or energy, right? That's what we think of when we think of radiation or radioactivity. We think of giving off particles and or energy. Energy being in the form of gamma radiation, particles being in the form of alpha particles, beta plus particles, beta minus particles, okay? Any nucleus with a ratio of neutrons to protons that falls outside the belt is unstable and decomposes. Okay, so 1.54 seems to be a limit to it. Then we have some examples. Okay, neutrons generate enough strong nuclear force to offset electrical repulsions by protons. If you have greater than 83, is stable. So no nuclide with Z greater than 83. So what is 83? Is that uranium? 83 is bismuth. Okay, uranium's more than that. Uranium's 92. So greater than bismuth? No. You can find things on the Earth, like we said, radium, thorium, and uranium, but all elements are unstable and eventually disintegrate into nuclei. Now they have long half-lives, and we'll get into half-lives later in this chapter. You see, this is quite an interesting chapter, I think. Consequently, the set of stable nuclei, those that make up the world of normal chemistry, is a small subset of all the possible nuclei. Okay. Okay, they talk about the strong nuclear forces. Okay, let's see. We have the belt of stability. I talked about that. If you just look at it before we get into the pathways that get us into stability, if you just do a rough analysis, you say that most of the nuclei that are stable, that fall along the belt, this is table 121.2, have an even number of protons and neutrons. So for example, oxygen 16, carbon 12, helium 4, those all have even numbers. There's 53 with an even number of protons and an odd number of neutrons. There's 50 with odd protons and even neutrons, like fluorine 19 has odd number of protons, 9, and 10 neutrons. Lithium 7, 3 protons, 4 neutrons. I can't think off the top of my head. You guys find one out, let me know. Even number of protons, odd number of neutrons. Okay. 30, what's 30? How about chlorine? No, chlorine's is 35. How about potassium's 19? Calcium. Okay, no, calcium's likes to be even. And then there's a few oddballs, literally, where it's odd number of protons and odd number of neutrons. Only 5 of those are stable. So the majority of stable nuclides are even. Does this add up to 100? 10, let's see, good. 11, 20, good. 3, 5, yeah, good. Okay. I thought there might have been some for the rhinoceros party. I made a joke. Okay. Oh, here's some examples. There's some of the odd ones. They're for the lightest elements, like hydrogen 1 is odd, lithium 6 is odd, boron 10 is odd, nitrogen 14 is odd, that's for sure. But above Z equals 7, there are 152 stable evens and just one, lanthanum 158, that is odd. Okay, so all we're doing there, not all we're doing, but what we're doing there is analyzing that belt of stability and what lies on it. So we'll see how that works in a minute. Write the symbols and determine for the following nuclei. Okay, let's do this together just for a bit of extra practice. So what's the first one? Oxygen nuclei with same number of neutrons and protons. So that's oxygen 16. Element 43 with 55 neutrons. Element 43 is an interesting one. That one has to be synthesized by humans. It doesn't appear naturally. That's why it's called technetium, and it is used in medicine for various radiation tracing systems. We'll get into that a little later in this chapter. So that's technetium-98, and then unstable nuclide of hydrogen with the lowest mass. Well, deuterium and regular hydrogen are stable, but when you go to tritium, then it isn't stable. Okay, then we have 21.12. Predict whether each of the following is stable or unstable. If you predict it's unstable, give you a reason. So 94 protons and 150 neutrons. Well, that is even Stevens. So you think, okay, that one could be stable, but look at this, it's got more than 83 protons, so that makes it unstable. What is 94? 94 is plutonium. Oh yeah, you don't want to mess with plutonium, that's for sure. The iodine nuclide was 73 neutrons. Well, iodine is 53 and 73, so that's odd. So most likely that particular isotope of iodine will not be stable. It'll be unstable and will want to decompose by some pathway, decay by some nuclear pathway as it tries to change into another isotope. We aren't saying how long it's going to take of iodine that will be closer to the belt of stability. Gadolinium, well, that's even. That's gadolinium 154. That's good. That's a good one. That one will be stable. Oxygen nuclide with 6 neutrons. So that'd be oxygen 8, 14. Typically, if you have less neutrons than protons, aside from hydrogen, which is super special, but less, starting in the second row, third, fourth, fifth, sixth, seventh row, you have less neutrons than protons, you are not going to be stable. Okay? Good. Now let's see this last one here. Fluorine has only one stable isotope. Compute the total binding energy and the binding energy per nucleon. Okay. Well, what the heck? Let's do it. So, well, I can't get it unless I know what the fluorine 19 isotopic mass is, right? Well, let's see. Is that written in the bulk of the pages here? I'm flipping back here, and I don't really want to Google this. Let's flip back again. I know they've talked about fluorine. Let's see, let's go back another page. I'm on page 1023. I'm looking for the isotopic mass of fluorine, and I don't see it. Let's see. Go back another page. Oh, that's the first page of the whole darn chapter. Oh, but here, what about on page 1023 near the end here? That's just a conversion factor. That's a picture at the bottom of page 1023, which shows the fluorine nucleus. That's very special. And then they have the example for helium. So they have left out the value for fluorine, which is swell. So I'm going to do something magical here. Watch this. Okay, I'm gonna go to the open up a tab here. Canada, Britain strike new trade deal. Great. Isotopic mass of fluorine, and I'm gonna write it down. Fluorine is all sorts of isotopes. That's great. Standard atomic weight. Well, if there's only one isotope, then that's what I'm going to deal with, right? Fluorine has 17 known isotopes? No, it doesn't. It just said one. Okay, geez. Okay. So isotopic mass of because I'm using Bing. No one wants to use Bing, do they? You can use Bing if you want, whatever you want. Okay. I want the fluorine 19 isotopic mass, right? Did you mean fluorine? Yes, that's what I meant. The stable isotope fluorine, okay, the stable one, fine. There's only one stable. Could be more than one isotope of fluorine, but only one stable one. So this is it, 18.998403. I'm going to write that down, 18.998403. Okay, now I'm going to close it off because I don't want to see it again. So I want to get the total binding energy, so I'm going to take the fluorine, 18.998403, minus 9 times whatever the protons are, plus 10 times whatever the neutrons' isotopic mass is, plus 9 times whatever the electrons is. And rather than writing all that in, I'm just going to write the answer there. I'm getting the numbers jumping back to page 1024, example 21.2, where the numbers are all listed there. So here we go. I'll say it out loud as I do it. 18.998403 minus 9 times 1.007276 plus 10 times the neutrons, 1.008665 plus 9 times whatever the electrons were, 0.0005486. I think I've written 0.00 before. That was the problem. And get a value minus 0.15, then multiply that by 2.73, sorry, 8.988, 10 to the 10, minus 1.4 by 10 to the 10. And good, that's right, hooray. Minus 1.43 by 10 to the 10th. Okay, and then I'm going to binding energy per nucleon. There's 19 nucleons, so if I divide by 19, I get minus 7.51, close enough, minus 7.52. 10 to the 8th, 1, 2, 3, 4, 5, 6, 7, 8. So that's so that looks good, okay? And you can your book will have those. I just want to go back to that one thing you can tell is bugging me about that fluorine question. Did I leave off a 0 on the? .0092109. Oh, see, look at this. Look at this. 0.00109. No, they still screwed it up. Okay. Oh, but no, that's uranium. That's not. I want to look at the fluorine. Let's go. Where's the fluorine one? Where's the fluorine one? Was way back. Oh no, it was uranium. Okay. Don't worry about it. Okay, but the one we just did, perfect. Together in class, let's make sure to do practice exercise 21.2 together, okay? And then we'll definitely know whether it was a typo or I was doing something wrong. And it's very rare for me to ever do something wrong, so I think it was them, not me. Okay. So one more little thing we'll do today, and then we'll call it a day. I just wanted to keep the that belt of stability in your mind there, because we want to know which way we want to go to get to that stability. So 21.2 in the nuclear decay, we have different processes. So unstable nuclides decompose spontaneously into others. So this is page 1028. Their nuclear decay, we have three features which characterize those decays. What are the products? How much energy is released, because you're always going to release energy, and the rate of the decay, how quickly things happen. And it's going to go back to first order chemical kinetics, which we are experts on from chapter 13, right? What are some products? Electrons, positrons, helium nuclei, helium-4 nuclei, which are called alpha particles, high energy photons, which are gamma ray photons. You release energy because the decay products are more stable than the starting materials. Okay. So what sort of things can happen? Well, you can have a neutron decaying into proton. Okay, and you have to have mass conserved in these nuclear reactions. Mass number and electrical charge are conserved. I should say mass number. Be careful. Mass number is conserved. So I can have a neutron inside the nucleus can decompose to a proton and an electron. Okay, so that is one way to try to make something more stable in the belt of stability. If you've got too many neutrons in that belt of stability picture on page 1027, if you have too many neutrons, then you may undergo this decay, which is called beta minus decay, or just beta decay, because you're seeing an electron is being spat out. You could also call it beta emission. The mass number is conserved, but total mass is not conserved, as we just saw. There's mass defects. Okay, so you can find out how much energy is released, and it's 7.5 by 10 to the 10 kilojoules per mole. Okay, so to balance this nuclear equation, you balance the total charge and the total mass number, right? So the total mass number, you got 1 on the left and 1 plus 0, which is 1 on the right. You got 0 is your atomic number for the neutron, and you got 1 for the proton, and the atomic number for electron is written as a -1. Okay, kids get tripped up with that sometimes, but in nuclear reactions, we write the electron as -1. Okay. I don't know why, you know, I have this iPad sitting by, like, far away from where I'm talking, and randomly, like once a day, Siri appears. I don't even have Siri activated. It's like it's possessing this iPad, and so you just heard me say the word atomic number, and now Siri started to tell me stuff about atomic numbers. It's a little scary, I think. I don't know. Maybe some of you don't find it too serious. Okay. Let's keep going here. What? Okay. Oh, there's too much fun happening here. Let's see. Yeah, we just calculated that, right? We got the mass of the proton plus the electron. Add those together, get the mass of the neutron, and subtract the proton and electron from the neutron, and you get that amount of energy. Okay. Ernest Rutherford, some guy, he studied all this, and he's from New Zealand, but he did work at McGill University in Montreal about uranium products, thorium, and he's the one who came up with alpha particle, beta particle, gamma particle designations. So pretty important guy. So here we see that we can have beta minus emission. Alpha emission, which is an alpha particle, can be spat out. This is for massive particles, or if your N over Z ratio is too large, you trying to get to the belt of stability. So this is one way to get to the belt of stability, because you're going to have now 2 less protons, but 4 less neutrons. No, I shouldn't say that. You're going to get twice the amount of no, let's see what's happening here. You're going to be losing some protons and some neutrons, right? And looking at the mass number, it's going to go down by 4, and the atomic number is also going to go down, but you want to get less n's. N over Z is too large. Okay, when I'm looking at the ratio of N to Z is too large. Okay, beta minus emission is another way to, I'm going to put a minus there, to get, you don't change your A value there, you do change delta Z of the emitter. Okay, delta Z of the emitter goes up by 1. So that is decreasing the neutron to proton ratio. I'm just looking at it there. Too many neutrons, too many protons. Okay. And then you can have beta plus emission. It's unstable because the ratio of N over Z is too small. You want to get it higher, so you want to emit a positron, and we'll go through that. And then there is electron capture, where you gobble up an electron in an orbit. So that's called orbital electron capture. And you can spit out an X-ray photon, and you see the changes in Z and A. And gamma emission, well, that happens all the time. You don't always write it all the time, but if it's the only thing that happens, you do, and that's when you have a gamma ray being created. An interesting side thing there, if you take a beta plus and a beta minus, you end up with pure energy. Okay, that's a matter and antimatter, a electron and an anti-electron, or electron and an anti-electron, an electron and a positron come together. So there's some weird and wonderful stuff happening here. But let's clarify this business about these ratios, too large and too small, because that can be tricky. So it's best to do that using some examples. So if nuclides are too massive to be stable, they lose mass by emitting helium nuclei, reducing the mass number by 4 because they're going to lose 2 protons and 2 neutrons. So the mass number is going down by 4, and the atomic number is going down by 2. So here's some example. You have samarium-146, and you're balancing it. It is an alpha emitter, so you get to neodymium-142 and 60 plus the alpha particle. So you see that 146 over 62 is 2.35. 142 divided by 60 is 2.37. So the ratios are different. Are we always going to have a ratio? I'm trying to see where this is more helpful. Let's look at the next one. Radon 222.86 goes to polonium 218.84 plus an alpha particle. So I'm going to do A over Z. 222. Oh, they're doing N over Z. Oh, Okay, not all books will do that way. 222 minus 86, so 222 minus 86, 136. So 136 divided by 86 is 1.58. And then I got polonium, so I do 218 minus 84. 134 divided by 84 is 1.595. And what was the other one? 222 minus 86 is 136 divided by 86. It's 1.58. So what we're doing here is actually increasing the ratio of N to Z. So nuclides that lie above the belt of stability have ratios of neutrons to protons that are too high. To become stable, these nuclides need to increase their nuclear charges. Such a nuclide converts a neutron into a proton. The nucleus expels the electron, thereby increasing its charge by 1 while leaving its mass number unchanged. So I'm looking in this region here. But it still isn't saying what to do to get the, it's just showing this is one of the processes, alpha emission. Then it's showing high N over Z ratio, low N over Z ratio. Okay, this is one of the most nasty drawings I've ever seen. Okay, I'll make sure I'll film about this instead. Here we have beta particles, or beta minus particles. So you can have hydrogen 3 go to helium 3 plus beta minus. So that is one possibility. We have PR145 go to ND145 plus a electron shot out. Gold 208 go to mercury 208 plus an electron shot out. Okay, so that's an example. If you have a nuclide that lies below the belt of stability, the neutron to proton ratios are low, and you want to reduce their nuclear charges. So you want to get more neutrons, and so what you do there is you can convert a proton into a neutron by positron emission. So here's some examples of positron emissions. Fluorine 18 goes to oxygen 18 plus a that's a typo. That should be +1, right? +1. I remember there were a few typos here. And then you got an iron example, you got an ND example. Okay. Another way to try to get towards the belt of stability is by using a nuclide with a low neutron to proton ratio, capturing an orbital electron, typically in the 1s orbital, because that's closest to the nucleus, so it just gobbles it up. That's called electron capture or orbital electron capture. And you use an E, you don't use a beta. Betas when things are happening in the nucleus. Okay. So we see some pretty pictures of things. We can have a positron emission. So beta plus can come out of a nucleus. We can have annihilation if a beta plus and an electron hit each other. We can have electron capture from an orbital. We can have a valence orbital can go into a 1s orbital and then be captured. There can be this whole process. It's called an Auger electron X-ray stuff going on. Okay. Then you can just have gamma rays just being formed if you have an excited nuclide, also called a metastable nuclide. You got a little m in it, being formed, and then typically once it's formed, it then loses that energy and it goes off, has gamma radiation. And you can have sequences of decay processes. Okay. You know what's interesting? They don't ask. This book has done. You know, I'm thinking about something that was done in our last book in terms of predicting what decay sequence will create will be preferred, and this book sidesteps it. That's interesting. I guess that means we don't have to know it, but I'm going to talk about it with you anyways because it's interesting. So, but I'm going to need another book, and I'll do that live in class. Okay. Let's see a decay sequence here. Radon-222 is got some possible bad stuff happening. We can have radon-222. We see that we can look at a 4-step sequence is what they want to do here. So they want you to lose an alpha particle, then an alpha particle, then a beta particle, and then another beta particle. Okay? So this is a typical question that I've seen on 2000 tests in the past. Okay, so you start with radon-226, you lose an alpha particle, so what's left is something with 84 and 218, which is polonium. Okay, then the polonium-218 is going to lose an alpha particle, so you're going to get lead-214, and then lead is going to lose a beta minus or an electron, it's spat out. So you're going to get bismuth 83, because 83 plus -1 is 82. The mass number doesn't change, 214. And then another beta minus comes out, and you get to polonium 214. And there may be others. These sequences stop when things get stable. So you can have a series of things happening. It's not just one kind of particle spat out, and automatically you're in the belt of stability. It can be more than one. It can be 10. Look at that. I'm not going to do this one. Practice exercise 21.4, where you're going to continue with 4 more steps. Okay? You can practice that one on your own. Rates of decay, that's a good place for us to start our next chapter. So that'll be Winnipeg University 21 lecture 2. Sounds good. Have fun. Practice all this.